Um, yeah, so let me very briefly introduce Juan. So Juan is a PhD here in the Quantum Thinker group in Delft, and today we will be presenting our recent work on gate-defined valley splitters in bilayer graphene. So yeah, Juan, the floor is yours.
Thank you very much, Antonio. And thanks everybody for being here in this afternoon. Today I will be presenting a recent work about gate-defined valley splitters in bilayer graphene, in which I work together with Kostas and Antonio that are here in the audience. And if you want to refer to the archive version, it's a very recent one shown here. So let's get started with our presentation today. And let's think about the main character of the story that we will be telling about today, and that is valleys in graphene. At low energies, the band structure of graphene has six points that cross the Fermi level, and these points that are far away in momentum space are so-called valleys. In order to connect and to move from one of these valleys to another one needs to have a scattering event that transforms the propagating state from one valley to another. One can think about these valleys as a spin degree of freedom, as a pseudo-spin, but for propagating modes, that is, for momentum space. However, because these are propagating states, controlling them is not as straightforward as is the case of a spin, where one can just think about magnetic fields. In order to control valleys, one needs to think about scattering, and that involves disorder, that involves edges, specific terminations, and that involves dislocations. However, just this very pristine picture is not an accurate picture of reality, because in reality, devices do not look like this, but they look much more complicated. And in particular, in order to realize such pristine structure with valleys, one needs to overcome some experimental challenges that arise in these devices. These challenges in particular refer to the cleanliness and the disorder of the electric fields and of the lattice structure of these graphene samples. And it has been only in recent years that experimentalists have been able to overcome these challenges, this disorder in these devices, and find very pristine and clean devices. In order to solve these inhomogeneities that appear in graphene devices, people have, first of all, found that encapsulation in hexagonal boron nitride is a really important part of the experiment. These are two hexagonal layers that encapsulate the graphene multi-layer structures. And because they are hexagonal as well, you have lattice alignment between these different structures, and you keep a two-dimensional plane of graphene quite protected and flat. On top of that, you need gates that define the electric fields that control the physics of graphene. And there are gates such as gold, for example, as you can see here on top in yellow, that these gates typically contain multi-grains with different orientations, and that even can be amorphous. And this is another source of disorder. So it's been as well in recent years that people have started to use graphite back gates, as you see here. Graphite is just an arrangement of several layers of graphene, and these as well are lattice aligned. Therefore, the structures that people use now are really clean structures that are as flat as possible and where the lattices are really aligned. Once that people have been able to find these really clean structures, they have been able to find cool phenomena in valley, and this phenomena involves all the degrees of freedom present in graphene. That is valleys and that is spin. And here I just show two very well-known cases that refer, for example, to the magic angle bilayer graphene that was found in recent years, and similarly to the strongly interacting phases that were found in Bernal stack bilayer graphene, also very recently. And these devices, we have an interplay between the physics of graphene, interactions, and spins. But nevertheless, these are bulk phenomena that are properties of a two-dimensional material. If one wants to fabricate something that is not bulk, if one wants to fabricate a nanostructure, one needs to start to adding confinement to these structures. And this is the point where we need to make a distinction between normal graphene and multi-layers of graphene. In normal graphene, it is not possible to open a gap at the valleys at the Fermi level. And that's why people used to cut the samples, to etch regions away and only define the regions that they wanted. However, as we saw before, this introduces disorder. This is a source of like scattering that we do not want in our devices. And that is where the properties of bilayer graphene come into play. Specifically because bilayer graphene has two layers. If one breaks the inversion symmetry by adding a displacement field, one opens a gap at the Fermi level that you can see here. I show three band structures and I increase the displacement field in them. And if you look at the gap, if you look at the Fermi level, there's a gap that is open in between the two levels, between the conduction and the valence band. And because this can be created with gates, now one can just use gates to define different regions in a single sample that either conduct or insulate. And then one can define more complicated devices, such as cavities, such as wires, and such as quantum dots. So moving forward, I will just list some of the devices that people have been working on, because this is a very big field, graphene and bilayer, and it's multi-layers. And I will start by referring to one-dimensional channels, conducting channels in bilayer graphene. What people typically do is that they combine the so-called split and channel gates in order to define a one-dimensional channel. As I mentioned before, by controlling the displacement field, one is able to gap specific regions of graphene. If one on top of that can control the chemical potential, one can just tune a specific region, as I show here, three gap regions, and only the region in the middle has electrons that are conducting and that are symmetric for both valleys. In this experiment, what people is able to find is that the conduction in these channels that are very narrow is quantized in units of 4 times the quantum of charge. That is because in graphene, you have 4-fold degeneracy due to valley and spin degrees of freedom. Furthermore, valleys are quite susceptible to out-of-plane fields because they are much more susceptible than spins. And that's why in these experiments, one can also observe a splitting of the different quantized levels as a function of the out-of-plane field. In what follows, I will be referring to this kind of channels as normal QPCs. That is in contrast to what are the so-called chiral QPCs. Chiral QPCs are devices where the direction of the displacement field changes. That is, you have a region where the field goes either up, connected to a region where it goes down. In between these two regions, there is a domain wall, and as is usual in physics, in this domain wall, you have a state that lives there. And these states are the so-called chiral states, that are states that close the gap and that live in an individual valley. We will look at these states in detail later, but for now, what you need to know is that while in the normal QPCs, you have a single backgate, that is a single layer of material, a single piece. In the chiral QPCs, you need to have 2 layers, 2 pieces of it, because you will have different electrical fields in them. One-dimensional channels are one of the kinds of devices that you can realize, and so are quantum dots in bilayer graphene. So this is, for example, a very well-known experiment of quantum dots, where you can see that as a function of magnetic field, you have a breaking of the 4-fold degeneracy. And because the theory predicts, you can identify the different levels as either K, K prime, and its corresponding spin configuration. And this is recently very interesting because there are some works that have found that you can have long-lived states in quantum dots in bilayer graphene. And these quantum dots can be either valley states, spin states, or a combination in the so-called Kramer's qubits that appear in these devices. And it's interesting because the relaxation times that have been found there are quite long. So that is something that brings interest to these devices. And we see that in all these devices, you have nice effects appearing due to the physics of valleys, but measuring them remains indirect in a way, because to measure valleys, you need to apply a magnetic field. Once you apply a magnetic field, the signal that you observe changes, and you identify the new signal in terms of what theory predicts, and you say this line is K and this other line is K prime, but you cannot really see a difference between the two signals. As you can see, for example, here in the resonant lines, they look very similar, but because of theory, we know one is K and the other is K prime. And there are also other experiments that are more specialized, but that require other ingredients. For example, the paper shown here in the right about collimation of states requires also lattice orientation, and it relies on the trigonal warping structure of the different valleys. But again, this requires a finite field. And furthermore, there are cases, as for example, in the case of interacting phases, where adding a magnetic field to the sample would break the physics of the states that we have, for example, in the case that these are zero field states. So with this thing in mind, we came up with the idea of proposing a Bally splitter. A Bally splitter, in its simplest terms, is shown in this picture. It has three regions where the displacement field is either positive or negative. If you look at the device from the left side, we have a normal quantum point contact where you have quantization along the propagation axis. Each one of these levels is fourfold degenerate, and you have incoming and outgoing states for both valleys. On the other hand, at the right side of the device, we have that the displacement field changes sign, and where it is exactly zero, a chiral channel forms. If you look at these channels, they have the interesting property that at each valley, the velocity of the channel is either along or against the channel direction. And you can look at that by looking at the derivative of this band structure. You see that it's either positive or negative for each valley, and that is reversed if we reverse the polarity, that is, if we reverse the regions with positive and negative displacement field. So in other words, the way in which this device works is you inject states that are a superposition of both valleys, and because of the structure in the displacement field, one valley can only go up and the other valley can only go down. And therefore, by measuring the difference in the current of these two leads, one is able to detect different valley phenomena or an imbalance in the valley that is coming into the splitter. So then, after proposing the device, we decided to do a basic characterization of it, which is a magnetotransport experiment. This magnetotransport experiment uses the fact that the valley G factor is very large, and if you use an out-of-plane field in a bilayer graphene device, it behaves very similar to a Zeeman field in a spin. In other words, it moves the two valleys up or down in energy depending on the sign of the field. So in the case of the left, for example, we have a field that is negative. And when this field is negative, one of the valley states will move up in energy. If we fix the chemical potential, we see that at some point, one of the valleys stops crossing the Fermi level and all the conducting states belong to one valley. If all the things that come into the valley splitter belong to one valley, then you see that the current has only one valley character, and the opposite is true for an out-of-plane field in the negative direction, with negative values. If you now change the chemical potential, you will find a region here in white where you have that the two valleys conduct, and because there is no imbalance in them, the current this expression cancels and you have zero. And then at some point, again, you will cross the next state, and then you will have an imbalance, and you will only be able to detect difference in the population of the states, of the valley states that you inject. So this is a first check of our device. But as I mentioned before, this device can be used to measure the valley physics of devices that are already being used and studied. And one of them is resonant transport. So previously, we saw that people do quantum dot experiments in these devices often, and typically they prove the current of them. So we decided to simulate a quantum dot experiment in which we just define a quantum dot in the middle of the normal QPC. This quantum dot is tunnel coupled to the lead, and we are able to observe resonant transport. So by applying an out-of-plane field, again, we will have a breaking of the fourfold degeneracy, and we will have levels that are valley polarized. And we perform transport simulations of the resonant transport through this dot. And in principle, one can see that the signal changes depending on the Valley state that you have. The signal is similar as the one that is already present in experiments. However, using this device, you do not need to interpret the signal as K or K prime, but you can actually see that it's a different valley because it comes out of a different lead, and the state might even be preserved if you can couple this device to something else. Furthermore, if you see at higher fields, around 0.3 Teslas, you can already start observing the splitting of the spin states, that they have a much smaller G factor than valleys. And however, this is an effect at finite fields. And I mentioned before that these devices can be used to measure valley phenomena at zero field. So then we continue checking the list of valley phenomena that we have. And one that is actually very interesting and has been studied recently is the one of intervalley coherence. So in order to simulate this, we got inspiration from the recent experiments of interacting phases in bilayer graphene, where it was found that there were regions that were intervalley coherence in the regime of parameters by tuning the different electric fields in the system. And looking into the literature, we found that in a tight binding model, intervalley coherence is often simulated using a Kekulé distortion, which is sort of like a charge density wave distortion in a region that couples valleys. And if we look at how the band structure in the reduced Brillouin zone now looks, as I show here in panel A, you can see that the two bands that correspond to the valley now hybridize. And around the gamma point, you have now a state that is a superposition of the two valleys. You could think about the intervalley coherence as some sort of Rashba, but in valley space. And similarly, if you look at the Fermi surface, at the valley expectation value of the Fermi surface, you can see that there are regions that are valley polarized, but at the center, it's unpolarized. So now what we define this, we decided that because so far now, it has only been shown intervalley coherence in bulk samples of interacting phases, we thought that in a cavity, which is sort of a large region, one could define intervalley coherence due to these interacting phases. So we decided to couple two valley splitters to a cavity that has intervalley coherence. So just to be clear here, in the middle, you have a region with intervalley coherence, and the splitters do not have intervalley coherence. But now, because they can be used in order to inject and measure current, we can inject valley polarized current. So for example, if we inject current from one of the leads in the bottom, that current will be only valley polarized. If the middle region does not have any intervalley coherence, and if the samples are clean, the current that goes at the other side should keep that valley polarization because, yeah, valley is a good quantum number. However, if this region has some sort of intervalley coherence, then the states that propagate through it will rotate in valley space. And that means that the current that goes out at the other side will go out through both leads. And this is a zero field effect that would measure intervalley coherence. So then we proceed to calculate what is just the transmitted current through this cavity as a function of the chemical potential and as a function of the phenomenological IBC term that we added here. Because this is a mesoscopic region, this is basically a chaotic cavity. So we cannot see specific levels or resonances, but we rather see just the interactions of all the scattering trajectories that happen between this cavity. But what is the most important thing that you can take out of this plot is that as a function of the IBC strength, you start to obtain a signal that comes from the two valleys. At zero IBC strength, you observe that the valley polarization, it's maximum at one valley. That means all the current that goes in stays in the same valley. As you start to increase the IBC, that current is no longer Valley polarized, but now comes out of the two leads because this quantity measures the current that comes out of both leads. And you can see that as this interaction is stronger, the average Valley polarization that you have as a function of chemical potential goes to zero, indicating that now you are mixing valleys. So here we have used the valley splitters in order to measure a valley phenomenon at zero field. However, there are constraints that our device has and limitations that must be taken into account when people want to think about fabricating these devices. The first one is the saturation of the helical channels. That means that because at the chiral channels, you only have 2 states per valley, or well, 4, counting the spin degeneracy. That is the maximum number of states that you can detect, and you can only detect differences that are up to that number. You cannot detect differences that are smaller, that are larger than that. And if you saturate the channels, it will be difficult to observe how many modes go into the splitter. That is one of the limitations. Another limitation that comes from the fabrication side is that in contrast to single chiral channels, now we have multiple chiral channels, and the gates underneath all of them need to be aligned. The back gate of graphite at the bottom needs to be aligned in order for the displacement field to be what we want it to be actually. So here I show how the displacement field on the top and on the bottom layer looks as for a given misalignment that here I call delta X, and in green I show the average potential. If we increase the misalignment, what happens is that we modify these channels, and now some normal states start to come inside of the gap given by the displacement field, and at some point this gap will close, and you will have normal states conducting along with your chiral states, and that is something that is detrimental for the transport. So the next thing that we did was to compute for different displacement fields what is the value of the gap and what is the maximum misalignment that can be tolerated between layers. And we found that for multiple misalignments, if you have for multiple displacement fields, if you have a misalignment on the order of 20 nanometers, this gap will become very small, will actually close, and you will no longer be able to transmit. But as long as the misalignment is sufficiently small, you will have that the energy gap is sufficiently robust to have a single chiral mode transmitting through it. Besides that, the last limitation or consideration that we have about this device is that it requires multiple layers of gates, and they need to be aligned, as I mentioned. And in particular, we were thinking about what structure would likely realize this valley splitter. How would the gates look like to realize this potential? And we could come up with the following gate structure that involves 4 layers of gates, which it requires to be fabricated, and it has many gates. So it's a concern that we have about it. But nevertheless, that brings me to the end of my presentation. And as an outlook, I can summarize and say that a valley splitter probes valley physics of confined structures and of open structures at zero and finite fields. Another consideration is that it is negatively affected by the gate misalignment because it closes the gap and brings propagating states inside of the chiral channels. And because current experiments typically create quantum point contacts, and there are also experiments with chiral channels, we think that it is possible to realize this device with current fabrication techniques that are available. But nevertheless, we are theorists. So thank you all very much for your attention. And if anybody has questions, I will be happy to answer.
I have a question, if I may. So
Yeah,
on your slide titled Probing Intervalley Coherence, was
yeah,
before you started talking about the limitations.
yeah.
Yeah, just in panel D, I was just surprised that there wasn't more gray area. And it seems that for many energies, the valley coherence is maintained very well, while there's this rather narrow band of energies in which the plot goes gray. And I was just wondering if you understood why or what gives rise to that narrow band, and why is the valley coherence seem so robust?
Yeah. We thought about this, and if you look at panel A at the band structure, um, you can observe that as you move in energy, if you go down in energy, the region with valley coherence, the region where the lines become white or gray, is only constrained to the bottom of these two bands, to the part where the two valley bands cross. And if you go away in energy, you again have that they are valley polarized states. So there's only this narrow region where we found that. However, it must be noted that we try to simulate this from a phenomenological perspective. It's this intervalley coherence is in an interacting system, and we're just trying to use single particle physics to mimic that. So there's also that caveat in mind, but it's because of that's the only part where the valley bands cross.
Yeah, may I add something here? In fact, the valley polarization is somewhat preserved all over the place. But you see that the average expectation value for valleys is actually decreasing. So it doesn't fully go to zero, mostly because if you look at the Fermi surface, the places where you actually have some valley coupling, which is the panel B, those white regions, those are the regions where you actually have strong valley coupling. But everywhere else, the valley number is somewhat well preserved. So you need some certain scattering events to actually mix the valleys. And those are the places where you actually get some decrease in the valley polarization. But overall, valley polarization kind of keeps, yeah, it's somewhat preserved. So we see this slow decay. It's not, it doesn't go to zero immediately.
Thank you.
Yeah.
May I ask you, the quantity that you discussed doesn't sound like valley coherence. It's more like valley memory. What do you put in term coherence? Usually, the word coherence appeals to those who talk about phase and maybe two-particle operation, in which you would have a coherent state which kind of loses its memory in terms of inelastic processes or something like this. The quantity that you describe here is more like kinetic parameter, which is like scattering rate. So that's the difference between T1 and T2 in quantum devices.
Yeah, no, exactly. If you would think about this okay, so first of all, in order to see some coherent effect, you would need an interferometer experiment where both valleys acquire a phase and you recombine and they interfere. If you think about it in terms of the Bloch sphere, that is basically rotating along the equator of the Bloch sphere. But in this case, we cannot rotate controllably along the equator, acquiring a phase. We can only know that we go to the equator. So we can create, we think that this can measure a superposition of valleys, but it is true, as you mentioned, that it doesn't measure the coherence of that valley superposition, the relative phase between them. It only measures the transport. We thought about how to recombine these two valley states in such a way that they become coherent again. But so far we couldn't come up with anything. But yeah, you are right.
And in the computations, what what do you assume about the scattering processes that change the valley state, or scattering processes at the edges? How do you describe them?
We have we assume that the samples are ballistic, so we have no scattering from the edges. We assume that it's clean, and the only source of intervalley coherence is the order parameter that we add in the central cavity. Everything else, we checked that it was that it did not add any scattering between valleys. Also here, we don't have like lattice terminations because we assume that everything is electrostatically defined. So there are no edge modes or valley that connect the two valleys. Does that answer your question?
Yeah, more or less.
Yeah, thank you. Thank you for the question.